Swayam Prabha. Digital India. Educated India.
Yeah, let us review quickly what you know on the state space technique so that we'll go forward applying this. Of course, we had already discussed a few of the points. We will just put down all the equations just to revise what all you've done in the previous classes on controls. Okay, so this all of you know, this is the response y of t. Okay, and the impulse response function, and this is the convolution term. You know the convolution part of the response, which when we take the Laplace transform of that equation, you get the multiplication of this convolution term or convolution integral. And we also saw that the Laplace transform of e power at is si minus a inverse, right? And that the g of s, which is the impulse transfer function, is given by this equation. Go back and look at it. D is usually equal to 0 in our cases, so that can go off. Okay, and very standard equation comes from, remember, x dot is equal to ax plus bu, y of t is equal to cx plus du. Okay, from that we get this. And the poles of the system are determined from this determinant equal to 0. Okay, and you know the importance of poles. And once, let's call P1, P2 be the poles of the system. Okay, and if P1, P2 are the poles of the system, then GFS is written say for example in partial fraction form, and that if you now take the inverse Laplace transform, you get g of t, okay, which is given by this function. In other words, the poles play a role, okay, which are loosely called as the eigenvalues of this things, poles or eigenvalues. One of the questions which people have, especially when they come from a vibration background, is that of the connection between the natural frequency and these poles. Okay, there's always a confusion as to what we mean by natural frequency and damping. In other words, the poles of the system are expressed in a slightly different fashion, okay, as omega n and zeta. For example, omega is the natural frequency and zeta is the damping ratio. So the relationship between, say for example, if the poles, of course you know that it has to be a complex conjugate, okay, or it can be only real, in which case you are looking at the time for relaxation 0.66 and so on, that is given by this time. And more importantly, if you want to pick the relationship between the poles, the natural frequency and damping, then the relationship is given by this form. Okay. So it is, people usually say that natural frequency is the eigenvalue or poles and so on. They are not strictly correct. Yes, one comes from the other, but please note that if these are the poles, okay, the complex conjugate poles, then this is what is the natural frequency. Okay, now you understand the natural frequency and the poles, what are important. Okay. Further than this, about the effect of poles, you all know it, and that you know that in the S plane, okay, if this is the left of S plane, okay, then if the poles are situated in the left of S plane, the system is stable, basically because you have this e power term here, and hence when it is negative, okay, the e power minus term, minus into t, would now start decreasing with time, and hence, okay, the system becomes stable. Okay. Electrical engineers have very interesting analogy, or very interesting way of interpretation, not analogy, very interesting way of interpretation, how they interpret this. So this is the j omega. Okay. So you would notice that if I want to look at the frequency response, what is that I do? I replace S by j omega, right? In other words, when I want to plot the frequency response, then what do? I plot omega here, okay, and the response in the y direction, or in the y axis. So you would notice that actually as I go along omega, I go up that axis, okay. At various places, okay, I go up this axis. As I go up the axis, if you look at what actually I calculate, okay, I calculate the distances between the poles, okay, between that point and the poles. That is what is meant by the denominator. Actually, that's the distance. You would notice that as I go along, okay, above this, and when I come to a minimum distance point, okay, assuming that these distances are large to the other pole, the distances are large, okay, since it is in the denominator, okay, as I move along omega, my response actually keeps increasing because the distance keeps decreasing, okay. So when I come to this point, because as I go, remember, as I go along omega, actually I'm going above in the y-axis. So when the distance is least, I get the maximum response, okay. In other words, that's why you have that, remember, that's the omega that you would get the maximum response. So then as I move away, the response now starts dropping, okay. So when there is no real term, which means that your poles lie on the imaginary axis, what would happen? That it would go to infinity, and so you would have a graph which goes like that and comes down. So this is another interpretation, okay, especially used in filter design, where it's very simple to understand, okay, the filters, which is low pass filter or high pass filter or band pass filter, for example, okay, those things can be, band pass filter can be understood very easily by these distances, okay, which are in the denominator, right, and which 1 by the denominator, 1 by the distance is small, then the response is large, okay. After all, you're looking at the response in the left hand side. Okay, so that's a neat interpretation for the frequency response function. Okay, in the last class, any questions? Okay, please revise once the state space formulation if you have any doubts. Okay, in the last class we were looking at, remember, the transfer functions, right? We said that the two important transfer functions that we had looked at is for lateral acceleration, okay. Lateral acceleration, in fact, what we did was to find out the lateral acceleration versus delta front, okay, as well as, what's the other one we did? R by delta. So I can write this as AY, just for simplicity, AY by delta and R by delta. Remember that we had only the front delta F and so on. Right. Now, we also, if I remember right, we also wrote down the steady state gain, okay, right? We wrote down the steady state gain. So steady state gain at S is equal to 0 is U squared divided by L into 1 plus K U squared, and that is equal to U divided by L into 1 plus K U squared. Right? This is what we wrote down. Right. Now what I'm going to do is to apply whatever we have done here, okay, to whatever we have done so far. In other words, I am interested to find out the poles of the system and then determine the omega n and the damping characteristics of the system. This is what I'm going to do now. Okay? Why are we doing this? Remember in the last class, we said that we need to understand this whole concept of the response from an objective perspective. Okay? From an objective perspective, and hence we need to understand how actually the system behaves, okay, and can be written in terms of omega n and delta. Okay, I'm going to write down now a series of equations, very simple algebra. Okay, so I'm not going to derive that step by step because that's going to take a lot of time. So I'm going to write down all these equations because interpretation becomes important. So I'm going to do that later. Okay. One of the things I promised that we have to look at also what are called as the zeros. Right? What are zeros? The numerator, okay, the same what you did with the denominator, you do that with the numerator. Okay? We have not looked at the zeros yet. We'll have a very interesting thing. What happens to the zeros? That we will do it, okay, after we finish this derivation. We are going to follow for objective. There are a number of objective metrics as they are called. We are going to follow this paper by Mimuro et al. SAE 901734. This is not the only way of looking at objective evaluation, but it looks, quite simple, quite appealing, and hence I am taking this paper. Right? So the first step, let me write down what all you already have it, so I don't have it in memory, so I'm going to write down what is A matrix for our problem. If there is any doubt, go back and refer. These are all there in your notes. Right? So this is A. Actually, if you look at literature, there's a lot of confusion on the C alpha F and alpha R. I was looking at a thesis the other day. There's a lot of confusion. People have put C alpha F and alpha R to be negative. Okay? In the signs are given in such a fashion that C alpha F and C alpha R are given as negative, in which case the whole understeer oversteer gradient definitions change. Okay? So this looks like an accepted practice, but I would like to warn you that when you read a paper or a book, be clear, okay, like how is this definition or given? What is this definition? We had taken minus alpha F so that ultimately that equation becomes plus C alpha F. Okay, sorry, we've taken minus alpha F, and so C alpha F, we had kept it as positive, okay, so that we get the force, centripetal force accordingly. But there are people who have written this alpha f to be positive and written C alpha f to be negative, okay, in which case their K definition would change and so on. Just a bit of warning. So when you read a book, ultimately everything would boil down to the same thing, but then the same interpretations. But then you have to be careful on the science, because when you do a problem or you want to understand it, things would be different. You have to be careful on that. Right. So the next step is Si minus A. Put that here, C alpha f plus C alpha r divided by mu, AC alpha f minus BC alpha r divided by mu plus u, AC alpha f minus BC alpha r divided by IZ u S plus A squared C alpha f plus B squared C alpha r divided by IZ u. Okay, so that makes my Si minus A. So the determinant of Si minus A is equal to 0 is what I have to find out. Okay, that is my next step. I'm going to do that. Modern vehicle dynamics follows the language of controls very closely. In fact, if you look at older books, okay, the approach would be very different. State space approach is usually not followed in older vehicle dynamics books. But today, because of the importance of automotive controls, most people have shifted to the language of controls, and hence we are talking the language of state space. Okay? Makes also very this whole subject to be very elegant, because you're just applying what you studied in controls to vehicle dynamics. So determinant of Si minus A is my next step. Do that, follow me, and I hope I'm correct. S squared plus C alpha f plus C alpha r, one step I'm just removing it, mu plus A squared C alpha f plus B squared C alpha r divided by Iz to U S plus C alpha f plus C alpha r divided by mu into A squared C alpha f plus B squared C alpha r divided by IZU minus, this is the last term, minus A C alpha f minus B C alpha r divided by IZ mu minus U into AC alpha f minus BC alpha r divided by Iz U. I hope it's correct. Yeah. Just check this. I think I'm correct on that. Yeah. Not very difficult to check. Just check that. Which one? The this will become S plus, so S plus C alpha F C alpha R S squared, correct? Then S C alpha F alpha R by mu, right? Plus A squared C alpha F plus IZU, yeah, yes, right? Plus C alpha F C alpha R, that's the last term is from there, U into plus, so minus is taken out, so that would be minus is outside this one. No, what's your, which one? This term? Ah. Right. Clear? Okay. The problem is there are so many terms, you have to be careful. There's nothing very difficult about it. Yes, right. Most of the times m is usually accompanied by u squared. You're right. Okay? That should be the case. Now let us concentrate on this last term. Okay, let me simplify this last term. Okay, that's what I'm going to do. Simplify it for me. Simplify this for me. So this would be, just follow me, very good, excellent. Just follow me whether all my steps are right. So a squared c alpha f squared plus, I know the last step is correct, but let's see that all the steps are correct, plus b squared c alpha f c alpha r divided by I m u squared minus a squared c alpha f squared plus b squared c alpha r squared minus 2ab c alpha f c alpha r minus m u squared ac alpha f plus m u squared bc alpha r whole thing divided by I m u squared. Right? Okay, simplify it. The beauty of it is ultimately, this is the third term, the last term. Okay. Ultimately, this happens to be L squared C alpha F C alpha R into 1 plus K U squared by I M U squared. Right? Check. Clear? Okay, you have to bear with me till we finish all this. Then we take the second term and I'm going to simplify it. Remember, what is my goal? My goal is to find out ultimately omega n and zeta. I want to find out the poles. From poles I can find out, or I'm going to develop a much simpler technique in order to find out the natural frequency and the damping ratio. Okay? Right? So the second term is, that's the term. So let me take m I z u squared as common. M, right? Sorry, m I z u as common. I z u as common. Okay? So the multiply the first term by I z, so that I get I z into C alpha f plus C alpha r, that is the first term, plus the second term is m into a squared C alpha f plus b squared C alpha r. Okay? That's the second term. Let me rearrange them so that I will write that as I z plus m a squared C alpha f plus I z plus m b squared into C alpha r divided by m I z into u. Right? Nothing difficult, just rearranging the term. So now I'm going to put these two terms, okay, simplified terms, into my determinant, okay, and write this down as a squared plus this whole term I z plus m a squared c alpha f plus I z m b squared c alpha r divided by m I z u s plus the last term L squared C alpha f C alpha r 1 plus k u squared divided by I m u squared is equal to 0. Okay, now from this I can find out the poles, okay, and then write down the omega n and the damping ratio zeta, right? I'm going to follow a slightly simpler technique, okay, which all of you know it. So I'm going to just write this in these terms, you know, which all of you know. I'm just going to write the final result because I want to quickly get into the interpretation part so that I can write this down as s squared by omega n squared plus 2 zeta s by omega n plus 1, okay, in this form. Write that last term in this form, right? From which, okay, when I rewrite that, anyway, that's equal to 0. So when I rewrite it in this form, I will get omega n to be 2L divided by U root of C alpha f C alpha r into 1 plus k u squared divided by I z into m, and zeta to be 1 by 2L into I z plus m a squared C alpha f I z plus m p squared C alpha r divided by root of I z into m C alpha f C alpha r into 1 plus k u squared. Okay, done. Now we will get into why we did this. Omega n will be 1 by, it won't be a, yeah, s squared, you just, see 2 zeta, note that it is 2 zeta omega n, so 1 by omega n squared, L squared, so L by, okay, I think, right, okay. Now why did we do this, or what is the, I hope I'm, just check, quite simple, just check whether it's okay. Now, here we pick up a physical interpretation. What is the physical interpretation of these things? There are 4 quantities of interest. One of the quantities, I'll write the expression later. There are 4 quantities of interest in this. One is what is, let me call that as A1. All of this we have already derived. Okay. One is what is called as the steady state response. Response of your velocity r. Remember what this quantity was? V divided by L into 1 plus k u squared, which we just now wrote. The second quantity of interest is omega n, okay, which is actually the natural frequency of the system. The third quantity of interest is damping. though Mimuro calls this as natural frequency of yaw and natural frequency of damping, I would resist from calling this because they are just the poles, okay, of the system. I wouldn't like to give them a name. Let's say that omega n is the natural frequency of the system. And then let me introduce a fourth quantity which I would call as phi, which is the phase lag at 1 hertz of lateral acceleration. Okay. Now, what is the physical meaning of the first one? I know the expressions now. Okay, so let's not worry about the expressions. If I give you a system, you'll be able to find out. So what is the physical meaning of steady state response of yaw velocity? Okay. What do you think is the steady state response to yaw velocity? What does it mean? That's a ratio between your R to delta. Okay. So higher it is, what does it mean? Easily R would be developed. Or in other words, you can interpret that to be the heading easiness. I want to head, how easy I am going to head. Okay? So in other words, how easily I am going to have the yaw for the car in order to get into the maneuver which I would like to have. So this would give you what is called as heading easiness. Right? Okay. Now, all of you know either natural frequency, either you can express it in terms of radians per second, or you can express it in terms of hertz. Okay? All of you know something about the natural frequency of the system. What is that you know about the natural frequency of the system? You know or you understand the responsiveness of the system. Okay? Clear? The larger the natural frequency, remember that in your earlier classes for a simple spring dashpot system, a second order system, okay, you were able to get what is the rise time, what is the peak time Tp, what is the settling time Ts, okay, overshoot, all those things. Remember that you did those things for a second order system, and that those were functions of 1 by omega n. Okay? So omega n, in other words, gives me the responsiveness of the system. Okay? Heading, for example, now it's heading because that's what we use the word heading in order to understand the maneuverability. So we get what is called as heading responsiveness of the system. Okay?
So can you please explain this?
Yeah, what is the, all the factors like settling time, okay, which is 4 divided by omega n into zeta, okay, and the peak time, all those factors are all functions of omega n. Okay, larger the omega n, smaller it is. Smaller is to say, for example, the peak time. So smaller the peak time means I will reach what I want faster. Okay, so it's ease with which I will go, or response of the system is now better when omega n is increased. Right? Damping, obviously all of us know it is responsiveness as well as there is a directional damping. So the guy won't oscillate. Larger it is, better that it would not get me an oscillating system. Right? And the last thing is the phase lag. What is the importance of phase? 1 hertz is because most of the systems have the frequencies of excitation, natural frequencies near 1 hertz, so 1 hertz is just given. But what is this phase lag? What does that tell you? What do you understand by the word phase lag? Or, pardon?
The response is a bit late.
Yes. So in other words, intuitively I know that if the phase lag is small, okay, what I give is immediately heard by the system or responded by the system, or in other words, it's easier for me to control the system. Okay? So I would call this as controllability. Right? So these are the 4, yes.
Is there a correlation between the phase lag and natural frequency?
No, this is for lateral acceleration. Phase lag of lateral. So how do I find this out? Remember we had the transfer function yesterday. Okay? In that transfer function we have to substitute S is equal to j omega, and then you would get that at 1 hertz, and that's what you would get. Now what Mimuro did, this is not very difficult physics, all of you know this. What Mimuro did was to plot this as a rhombus. He plotted this as a rhombus. So how did he do that? In a very, I would say, interesting fashion. Okay? He had the natural frequency Fn in one of the, see there's no 2 axes. Look at this carefully. The positive side he had Fn. He had phi increasing like this. Usually phi can be, say, minus 80, minus 40 and so on. Okay? That's how he plotted phi. Then he plotted the damping coefficient zeta in this axis. Right? And of course, the other one, A1 here. Why did he plot it like this? Very simple, that if I now plot that for a car like this, okay, it simply means that, understanding the physics of all these 4, it simply means that larger this rhombus is, larger means Fn is larger, good for me. Phi is larger, that means that look at how it is going, minus 40, minus 80, minus 40 and so on. Okay, it's usually the minus, and then okay, larger it is, which means that your, yes, the response is very fast, so that's a lag is small. Okay, larger it is, good for me, damping, and larger it is, my first term, which is the heading easiness, is better. So he simply said that plot this like this. When you plot it like this, then the larger this rhombus, the larger the rhombus, better is the vehicle handling. Simple. Okay? It's very easy to now understand, or else it's not, it is, yeah, you have to go into too much of details. But here, this is the first or the easiest way to understand vehicle handling. Look at the area of this rhombus, and I'm going to find out how good is my vehicle. Okay, but look at all the equations which I think maybe some of them I've written here, some of them you don't have. Here A1 and phi, okay, phase lag, I have to write down that equation. That's a tricky equation. Let me write down A1 also. So let me write down A1 here. A1, which you already have, U divided by L into 1 plus K U squared. And phi is arc tan A L C alpha R divided by L C alpha R U divided by 2 pi minus pi I Z U. That's a lengthy expression, but I want you to check this. Slightly doubtful whether there is a 2 here or not. Fn divided by Fn squared minus 1. Just check this. I think it should be right. But check whether that's correct. Now, there is one small, very small, one issue. What's the issue with all these expressions? What's the issue? The interesting issue here is that it not only depends upon the car, of course it depends upon the tires extensively. So the tires are going to play a great role in handling, no issues. Okay? In fact, we have, if you remember, we have linearized the tire performance or tire characteristics and just put that initial slope. Okay? Not bad, not the best way, because we need to get this other tire models. Okay? But we usually assume that we are not going to be away from the linear case. We will come to how he determined this experimentally in a minute. Okay? But before that, let's look at these things carefully. What are the peculiarities? Yes, this and this has an effect. But more importantly, the velocities seem to have an effect. Okay? The velocities are important. So all these things are functions of velocity. You had written down A, yeah, and velocities are important. In other words, a vehicle handling also depends upon the velocity. So if you want to test a vehicle, it's not enough if you test at 80 kilometers per hour. Or it's not enough if you draw this rhombus at 80 kilometers per hour. So we also need to plot that for different velocities. And what do you expect? Look at that carefully and tell me. What would happen to A1? What would happen to other factors for a particular K? Most instances, actually, with increase in velocity, V or U rather in our case, as we increase the velocity, rhombus now goes down. So in other words, the handling characteristics depend upon the velocity. A vehicle which performs very well at 80 kilometers per hour, okay, will see a deterioration with velocities. Yes.
How about even telling it will be a rhombus when you decrease?
Yes, the typical value. See, because I have this formula. Okay, we will do a problem in the during one of the assignments. I have all this formula here. Okay, I know the typical values of K. Just substitute it, vary it with the velocity. In fact, if in other words, if I want to now plot omega n versus, I need to do, say, what I need to do is to omega n versus u. If I now plot it, the graph would look something like this. Clear? So if I now plot each of these quantities with velocity, for example, omega n, if I plot, it would be like this. So now I get those. I have already the formulas there. I get those and then plot it here. Right? Very simple. Nothing very difficult. So now the other one is the understeered and the oversteered vehicle. How is the understeered and the oversteered vehicle going to be affected? Now what would happen to an understeered? How would, as the vehicle becomes more and more understeered, how will that go? Look at that formulas and tell me. As the big vehicle becomes understeer, what would increase? Okay, omega n would increase, A1 will decrease, so it will move like this. And obviously, the oversteered vehicles move in the opposite direction. Now, how did Mimuro determine for cars? In other words, what is the experiment he did or he recommended? This group recommended an experiment called the pulse steer. A pulse steer test. In a pulse steer test, in a matter of 0.4 seconds, a steering is given an input, okay, of about 60 degrees and back. So that's the pulse steer. You give a pulse actually to the system. Okay? So you give a pulse to the system. It's like giving an impulse. Okay? So the pulse excites a number of frequencies, and that's the reason why we went to the pulse of the system. Right? Here we can look at Y pulse and so on from FFT point of view, but I'm not going to do that this class. But go back and read, and maybe when you have time, the later part of the course, when we talk about ride and we talk about FFT, we will look at the beauty of that pulse. Okay? So he gave a pulse to the system and said that at least about in 0.4 seconds, okay, this was done. This was done so that the lateral acceleration are in the order of about 0.25 to 0.3, so that the assumption that we made regarding the tires, that they are linear, is valid. Clear? In fact, we have done a lot of work on this, and we found that this, with an expert driver, this rhombus, okay, which we call as Mimuro rhombus, and the subjective evaluation of a driver matched very closely. So in other words, we found this to be an excellent objective evaluation tool. All right? So now you see the importance of tires, and we will see the importance of other things, okay, as to how they're going to be affected. Right. Any questions?
You said variation, we know the variation of say omega n with respect to like, but say omega a1 varies with u by 1 plus ku square.
Yeah, depending upon the value of k, this would vary, and so I know the k values that you have.
Root over 1 plus ku square by u. So it's like inversely proportional. How do you think rhombus will be there? What if it intersects with our ideal case?
Come again? What I suggest is that, okay, I understand that how much it would vary. We will do a problem. Okay? That is the easiest way to understand it. Okay? How, for example, you're asking how big is the k? Okay? Would it have an effect, okay, if k is large or small? Right? We are talking about a typical car. What is the k value? Which is an understeer coefficient car. Okay? So what we will do is maybe we will do that in the next class. Okay, I will work out and I'll put some values to this so that you will understand how exactly that varies. You know, that's your doubt, how much it varies. We will put typical values in the next class, and we will, okay, work out a problem that would give you an idea as to how it varies. Right.
Can you explain a bit more about the experimental setup?
In fact, the experimental setup or the experiment, okay, we will do that maybe in the next class. This experiment, you will do it in your vehicle dynamics lab class. Okay? You will do this in the lab class, so that's the reason why there's a lot of experiments that need to be explained. You know, this course is too short, we can't do everything here. So this course is more on theory. The experimental vehicle dynamics you will do in vehicle dynamics lab. Right? Anyway, we will pick up, we'll give you some dope on this in the next class. Okay. I'm going to give you an exercise. Okay, do this. You remember that we defined beta Okay, V by U, remember that. Find out an expression for the transfer function for beta. Okay, that will be an exercise and we will follow it up in the next class. Stop here and we'll follow it.